Okay, let's begin our lesson. So right now we already show you we have at least 5 kinds of CVD, and the first two APCVD, LPCVD, and LD. The first three, and LD is belong to the first kind of CVD. Or it means the only energy will be the thermal energy. Okay, so it requires the high deposition temperature. Okay. And the second kind of CVD includes PECVD, HDPCVD, and PEALD. So those 3 kinds of CVD have both thermal energy and the plasma energy. So that's the reason the deposition temperature is much lower. Okay. Later we will go back to see to compare between different kinds of CVD. Let's begin to talk about the APCVD, okay? So APCVD is the first type of the CVD in industry we use. Many years ago, it's the first type. Because you see, we don't require the vacuum system. 它们不用有那些抽真空的设备。It doesn't require the vacuum system. So that's a reason it's a very simple reactor. So it's the first type of CVD we use in the IC fab, okay? However, the main drawback of the APCVD will be the low diffusivity of the precursor, the low diffusivity of the reactant, okay? Due to the shorter mean free path. What does that mean? Right now you know low diffusivity of the reactant, right? So today, for example, if I want to deposit this, if the target something is the silicon, I want to deposit the silicon, and what is the precursor? Precursor is the SiH4, right? Silane is the precursor for the silicon, right? So our target something is the silicon. I want to deposit the silicon, and today the precursor is the silane. Okay, so right now, I just input the silane into the chamber. But however, due to the 1 ATM of the chamber, so it means we have many air. We have many air inside the chamber, right? We have a lot of air inside the chamber. Okay, so today, when we put the silane into the chamber, what happens? The silane will bombard to the air. Okay, and right now, maybe I can write down the distance is the S1. The distance between the first collision will be the S1. 第一次碰撞的距离是 S1. Then the silane will collide with the second air. Air maybe oxygen, maybe nitrogen. So the second collision, the distance will be S2. Okay. Then the silane will bombard to the third air particle, whatever, and the distance is the S3. So the mean free path, the average mean free path, just S1 plus S2. Plus S2 plus S3 and divided by 3, okay? I just want to show you mean free path. Mean free path means the average distance between 2 collisions, okay? The average distance between 2 collisions. So I use this example just shows you the average distance between 2 collisions. 两个碰撞之间的距离是个平均距离。Because inside the chamber I have so many air. We have so many air inside the chamber due to 1 ATM. Due to 1 ATM, the pressure is 1 ATM. Therefore, we have so many oxygen, nitrogen inside the chamber. And the silane, when we input the silane into the chamber, silane will collide with 撞击 will collide with all of this air. Okay, so you see, for the silicon, for the substrate, for our silicon substrate, do we have enough silane or not? we don't have a lot of silane. We don't have enough silane, because the silane will collide with the air, the silane will collide with the air, so the silane will not easily to go down to the silicon surface, because the silane will bombard to air, right? Bombarded to air. So we don't have enough silane. We don't have enough silane on the silicon wafer surface, because the silane is not easy to fall down on the silicon wafer, because we have so many air between the silane and the silicon wafer. Okay, so that's the reason we mentioned low diffusivity of the reactant of the silane. Okay, silane is collide with the air, so silane is not easy to fall down on the top of the silicon wafer. Okay, so right now you know we don't have a lot of precursor. We don't have a lot of silane. Silane is not enough. Okay, so of course, APCVD generally operate in the mass transport limit. It means APCVD is always operate in the region of the diffusion rate control. Diffusion rate of the silane control the deposition rate of, okay? Diffusion rate of the silane. Diffusion rate of the silane control the growth rate, okay? Control the growth rate, okay? So because we don't have enough silane on the top of the silicon wafer, so that's the reason we say, right now the mechanism will be diffusion rate control. Diffusion rate of the silane control the growth rate of the silicon, okay? So right now, if we can have the uniform gas flow rate over the each wafer, then the uniformity of the growth rate will be better. So right now, the flow rate is very, very important, not the temperature, because right now we already have high pressure. But one thing is missing. The reactant is not enough. Okay. So today, if the flow rate is higher, and also the flow rate is uniform, then we can have the uniform growth rate. Okay. So that's the reason. All of the silicon wafer must be laid flat on the horizontal surface, because we want to make sure each wafer has the uniform gas flow. Okay, we want to make sure we have the uniform gas flow across the wafer. So the wafer must lay flat on the horizontal surface. What does that mean? You can see here. This is the reactor. This is the reactor of the APCVD. So we have the reactant gas, the pipe for the reactant gas, and the red color here is the wafer. Okay. Right now we only operate one single wafer. Okay. But you see how the gas flow is very uniform across the silicon wafer, because we want to make sure we have a very uniform thickness. We want to make sure we have the uniform growth rate. So we need to make sure we have the uniform gas flow across one single wafer. So this is the single wafer system. One time we only can deposit one single wafer, and we need to make sure for this single wafer, the gas flow, the reactant gas flow is very uniform across the whole silicon wafer. Okay. So one time only one single wafer. Okay. So let you see how the silicon wafer is laid flat, right? The silicon wafer is laid flat inside the chamber lay flat because we need to make sure the gas flow is uniform. Okay. So here, we need to make sure our gas flow is uniform in order to have the uniform. In order to have the uniform thickness, okay, across the one single wafer, okay. We want the gas flow is very uniform across the one single wafer in order to have the uniform growth rate and which can result in the uniform thickness across one single wafer, okay? So of course, this is the single wafer system. It cannot use the batch system because you need to control the uniformity of the gas flow, okay? 这边我们跟同学说它的这个 gas flow 它的这些气流的均匀性必须要很好，所以它一次只能做一片 wafer， 它确保在这一片 wafer 上面所有的 gas flow 都是 uniform， 这样才能够确保它在这一片 wafer 上面所有的地方它的 growth rate 这薄膜的沉积速度都是均匀的最后我们才会有均匀的厚度那我现在讲的均匀性是指在一片 wafer 之内。它的均匀性要控制好的话，那你的 gas flow 在这一整片12寸的晶圆上面，它的 gas flow 都必须要是非常均匀的 ，OK？ And also, at any given time, there may not be sufficient gas present at the wafer surface. It means we don't have enough reactant, we don't have enough reactant. So high gas flow is required. High gas flow is required. Okay, so it just means due to the diffusion rate control, if we can increase the gas flow, the growth rate can be enhanced. Okay, the growth rate can be enhanced. Right now the temperature is not an important factor to affect the growth rate. Okay, right now the gas flow rate is much more important. If you have a higher flow rate, the growth rate can also be enhanced. Okay, so as we mentioned, you need to have a higher gas flow rate and also very uniform gas flow rate. Okay, you need to have a uniform gas flow rate, and also you need to increase the flow rate. Okay, in order to have a higher growth rate. Okay. Okay, and however, this kind of tool, like the APCVD, usually it will have the poor step coverage. It will have the poor step coverage. So, as we mentioned, today we have a change. And we want to deposit the same thing on the top of the change. And usually, the precursor will remain here. Because this angle, this contact angle is larger. So usually, for the APCVD, the precursor will remain mainly on the top corner here. So it will result in the overhang on the top corner. Okay. So we say it will have the overhang, overhang. Okay. So we say APCVD usually APCVD fin will result in poor step coverage. So for the top corner, the fin thickness is thicker, so it will result in the overhang in the top corner. Okay. And when we talk about APCVD, we need to talk about LPCVD later. Okay. So for the APCVD, the reactor is very simple. Of course, we don't need the vacuum system, right? So therefore, the reactor is quite simple 吼 ，it's very very simple 吼，因为这边我们不用把它抽真空吼，你不用粗抽细抽，那所以你的这个腔体设计一定很简单嘛，因为它是常压，它不用抽真空，不用抽到10⁻⁹次方透，所以它当然它的至少 reactor 为什么简单？你只要想它不用抽到10⁻⁹次方，它也不用细抽哦，就是它不用这些不用这些 pump 把它抽到一个很高的真空度吼，所以它的 chamber 一定是很简单 ，OK？ 哦，它只要用这个conveyor conveyor belt 哦 ，they only use the conveyor belt to transport the silicon wafer. Oh, so the reactor is very simple, okay? Because it doesn't require the pumping system, okay? Okay, when we talk about the precursor, right now for those two following pages, we are talking about the precursor, the reactant here, okay? So many years ago, the most common use of the APCVD is the deposition of the SiO2. At the time, for the SiO2, we use the TSO long. What is the TIOS? The TIOS here. We have the chemical solution here for the TIOS. TIOS is very important. So for this slide, I can show you, I show you the precursor is important because nowadays we still use this precursor, but we don't use APCVD and we don't use APCVD for STI gap filling or ILD. The tool is wrong, but however, precursor is accurate. So you need to memorize precursor, okay? So right now, for the precursor TIOS, you see, we have the silicon here, the silicon. We have the silicon, and we have C2H5O. You see, C2H5O, okay? So we have four C2H5O, right? 1, 2, 3, 4. We have 4 C2H5O, okay? So you see, the TIOS, this is the chemical, this is the atomic structure for the TIOS. So silicon and C2H5O, C2H5O, and we have 4. 1, 2, 3, 4, right? Quite simple, right? This is TIOS. So the precursor of the TIOS can provide the silicon, okay? Also, it can provide the oxygen, right? Because the TIOS has the silicon, and also the TIOS has the oxygen, right? And how about O-long? Why is O-long? O-long is O3, right? So O-long can provide the oxygen, right? O-long can provide the oxygen atom, right? So today, if our target same thing is the SiO2, I want to deposit silicon dioxide, SiO2. If I want to deposit the silicon dioxide, the TIOS O-long is a very good choice, right? For the TIOS, the TIOS is the source for silicon, also the source for the oxygen. And O-long can also provide the oxygen, right? So this precursor is important. TIOS, we use TIOS a lot in IC fab, okay? But one thing you need to know, right now we don't use APCVD, and APCVD is not used for the STI gap filling and ILD, okay? Tool is not right. We don't use APCVD, and we don't use APCVD for the STI gap filling and ILD, okay? Because our textbook, right, is for when the technology not larger than 0.25 micrometer, okay? So it's not useful for right now, okay? But let me ask you a question. Let me ask you a question. So today, if I want to deposit, or if I want to deposit the silicon, or like the polysilicon gate, when the technology node is larger than 28 nanometer. So can you tell me, we have two kinds of precursor, right? Today, if I want to deposit the polysilicon gate, when the technology node is 28, larger than 28 nanometer. So, we have two precursors. Do you remember? The precursor for the polysilicon gate. One is the silane, right? And the other one, right now you know the TIOS, right? Right now you know the TIOS can also provide the silicon, right? So can you tell me, today if you want to deposit the polysilicon gate by CVD, which precursor you will use? Which precursor you will use to deposit the polysilicon gate? Which one? Which one? Right now, I only want to deposit the silicon. I don't want to deposit the silicon dioxide. I want to deposit the polysilicon, the silicon. So do I want the oxygen or not? I don't want the oxygen. Okay, I don't want oxygen. Right now, I only want to deposit the polysilicon. Okay, so today, if you use the TIOS, you see, the TIOS has the silicon to oxygen bonding, and the bonding between silicon and the oxygen is very strong. Okay, so if you want to break down, you want to break down how the covalent bond between silicon and oxygen, it's not so easy, and it requires high temperature because you want to break down the covalent bond between silicon and the oxygen. Okay, so today if I want to deposit the pure silicon only, not oxygen, I will use the silane. I will use the silane for the precursor. I will not use the TIOS, okay? Because the TIOS has the oxygen, and it's not easy to break down the covalent bond between silicon and oxygen, okay? So today, if I want to deposit the polysilicon, I will use the silane. I will not use the TIOS because TIOS has a very strong SNO, silicon and oxygen bonding, okay? So it means, it's not easy to have the pure silicon precursor, okay? Because the covalent bond is so strong, okay? So it's better to use the silane to deposit the silicon, okay? If you want to deposit the silicon, you use silane, okay? So the next question will be, right now, if I want to deposit SiO2, silicon dioxide, so why the industry want to use TIOS alone, rather than silane and alone? Why? This is the next question. The next question, right now I want to deposit the SiO2. Why the industry use TIOS alone? They don't want to use silane alone. Why? Let's take a look for the next chapter to answer your question here, okay? So I highlight here, if you want to deposit the SiO2, you need to use the TIOS and alone, okay? And the reason why we use this slide to show you, okay? Okay, let's introduce the TIOS. TIOS is a liquid organic precursor, and O-Long is much more reactive than O2, okay? So some process, if we want to use the oxygen atom, we will use the O-Long because O-Long is much more reactive than the oxygen, okay? So the process can be operated at lower temperature of 400 degrees Celsius, or even without plasma, because O-Long is very reactive. So the operation temperature, deposition temperature can be as low as 400 degrees Celsius, okay? And then the next one. Why do we use the TIOS plus O-Long? Why don't we use the silane plus O-Long or O2? to deposit the silicon dioxide, Today, our target thin film is the silicon dioxide. Why we prefer to use the TEOS, okay? Oh, so right now you see, the TEOS have high surface migration. High surface migration, it means the TEOS, this precursor has low sticking coefficient. 它的粘滞系数、粘着系数比较低。TEOS has low sticking coefficient, so it means it has long mean-free path. It means TEOS, this precursor, have the higher mobility. This precursor can move around. So the film has the excellent step coverage. Okay, so let me show you the gap. Right now, I have a gap or a change. Okay, so today the TEOS, I use the blue color to show you the TEOS. Okay, so this is the precursor for the TEOS. Today, the TEOS has a low sticking coefficient. It means, right now, although the TEOS is on the top corner here, today, although the TEOS is on the top corner, for the precursor is very easy to remain in the top corner because top corner has the large contact angle. So the precursor is very easy to remain or to stay in the top corner. However, the TEOS has low sticking coefficient. It means the TEOS has the higher mobility. The TEOS has higher mobility, right? Low sticking coefficient just means the mobility is higher. It's very easy to move. Mobility is higher. It means this precursor is very easy to move around. Okay. Therefore, this TEOS precursor can go down. Okay, can move. Can go down to the bottom corner. Okay. Because it has the high mobility and has the low sticking coefficient. So although the precursor remain on the top corner, this precursor TEOS can move down, can diffuse down to the bottom corner. Okay, so you see this SEM image. We can have the conformal step coverage. Okay, because the precursor will not remain on the top corner here. Okay, and right now you see the TEOS has the sticking coefficient about 10 to the power of -3. Okay, and then how about the silane and O2? Today, if I want to deposit the SiO2, you also can use silane and O2. But however, for the silane, you see, the sticking coefficient is higher. You see the sticking coefficient is higher. Let's take a look for SiH2 and the SiH. Okay. Although SiH4 is lower, SiH3 is also lower. But however, you see SiH2 and SiH, those two sticking coefficient is higher. Those two, and maybe this one, the sticking coefficient is higher. So what does that mean? Today we also has the change here. And then when the silane remain here, silane will not move. Silane will not move. You see, the silane will not move around. Okay, because the sticking coefficient is very high. So the mobility of the SiH3, SiH2, and SiH is very, very high. So they will not move. Okay. So maybe I can modify SiH3. SiH2 or SiH. Okay. All of these precursor, when all of those three precursors remain on the top corner, it will remain, it will not go down to the bottom corner, because all of those three precursors will remain on the top corner due to the high sticking coefficient. So it means those three precursors have very low mobility. 这三种 precursor SiH2、SiH3、SiH 这三种 precursor 因为它具有高的 sticking coefficient， 就是它的粘滞系数很高，你把它当一个粘着系数，粘滞系数很高，所以它一旦碰到上面的角落最容易碰到嘛，因为它的接触角270度最大，所以上面两个 top corner 它最容易碰到。那这三种 precursor 一旦碰到，它就不动了，所以我们说它有很高的 sticking coefficient。那代表它的移动能力差不差？它的移动能力很差，这三个移动能力很差，所以它不会往下跑，是不是代表所有的 silicon 都沉积在哪里？都沉积在 top corner， 所以 bottom corner 的地方，它的薄膜是不是变得很薄？So later you will see. So later we will have the overhang. Later we will have the overhang. So you see. So later we will have the overhang for the silane. Okay. Later we will have the overhang when we use the silane O2 to deposit the silicon dioxide. We will have on the top corner here and here we will have the overhang. So we say the step coverage for the silane and O2 is poor. Okay, step coverage is poor for the silane and O2. So that's the reason if I want to deposit the silicon dioxide, I will choose tears and oolong. Okay. Today, if I want to deposit the SiO2, I will choose tears and oolong. And the reason is we will have the excellent or conformal step coverage. Okay. The main reason we choose tears oolong to deposit the silicon dioxide because we can have the excellent, it means conformal step coverage. Okay, so that's the reason we don't use the silane and O2. Okay, so far so good. So those two pages I show you, the precursor is important. You need to remember the precursor. Okay. And APCVD, we don't use it right now. So just for your reference, to let you know the APCVD due to a lot of air. So it's the diffusion rate control because we don't have enough silane on the top of the silicon wafer. Okay, so you need to know the mechanism, and also you need to know the precursor for the oxide and the precursor for the silicon. Okay. Okay, right now we go down to see the LPCVD low pressure. So those two CVD usually we can compare between each other because low pressure means we don't have air, right? Low pressure we don't have the air, and the AP atmospheric pressure means we have a lot of air, right? So those two kinds of CVD usually we will compare together. Okay. So for the LP CVD, right now the benefit for the LP CVD will be the much higher diffusivity of the precursor due to the longer mean free path. Okay, you just need to compare LP CVD with the AP CVD because we don't have the air in the LP CVD because it's the low pressure chamber. So the high diffusivity of the reactant, okay? So it has the better transport of the reactant, because the reactant will not collide with the air, okay? So the high diffusivity of the reactant, okay? Reactant has the higher diffusivity. The reactant will not collide with the air, okay? Also, we can remove the byproduct more easily, right? Or we can remove byproduct more easily because no air. So today, we want to transport the reactant, it's easy. And if I want to remove the byproduct, it's also easy because we don't have a lot of air inside the chamber, right? We don't have a lot of air inside the chamber, right? Or here, APCVD, we have a lot of air. We have a lot of air inside the chamber. So the precursor is not easy transport to the silicon surface. And the byproduct is also not easy to pump away, okay? However, it's not an issue. It's not an issue for the PCV or for the LPCVD, okay? Or because we can easy to transport the reactant, we can also easy to remove the byproduct, okay? So right now we have a lot of precursor, we have a lot of reactant on the silicon surface, okay? Or right now we have a lot of precursor on the silicon surface. So right now it's the substrate or silicon substrate, and the target thin film is also silicon. So the precursor is the silane, right? Because we don't have the air, so it's very easy. So the silane is very easy to transport to the silicon substrate, very, very easy, right? We have a lot of silane, So today, the growth rate limiting step is the reaction rate limited. Because we have a lot of silane, we have so many silane on the top of substrate, okay? We already have a lot of silane on the silicon wafer, okay? So right now, if I can increase the temperature, from 400 degrees Celsius to 500 degrees Celsius, the growth rate can be improved a lot, okay? So if you can increase the temperature from 400 to 500 degrees Celsius, the growth rate can improve a lot, okay? Because right now I have a lot of silane. On the top of the substrate. But right now, if you can increase the temperature a little bit, the growth rate can be enhanced a lot. So right now, this rate means the growth rate, means the deposition rate. Deposition rate is controlled by the reaction rate. Deposition rate is controlled by the reaction rate, okay? So right now, the uniformity of the temperature is important. Uniformity of the temperature is important because the temperature will determine the growth rate. So right now, high temperature is important, of course. High temperature is important, okay? Also, the uniform temperature is also important, okay? Okay, due to the reaction rate control the LPCVD, so if you want to have the higher growth rate, of course, high temperature is very important because we already have so many precursors. So the growth rate is determined by the reaction rate, okay? So today, high temperature can make sure we have the higher growth rate, okay? And today, in order to have the uniform thickness, we need to have the uniform temperature, okay? Uniform temperature can make sure we have the uniform thickness. Or we want to have the uniform thickness. We want to have the uniform thickness. So you need to make sure we have the uniform temperature. So everything about the temperature is so important, right? So no matter how, we need to have higher temperature. We need to have the uniform temperature in order to maintain the uniform thickness across the wafer to wafer, or the lot to lot, okay? Okay, so right now, the gas flow rate is not so important because we have a lot of reactant on the silicon wafer, right? So right now we can stack wafer vertically. We can stack wafer vertically. We don't need to put our silicon wafer, or we don't need to put our silicon wafer laid flat like the APCVD, because the gas flow is not so important right now. The gas flow is not important, so we can stack wafer vertically, okay, and also closely inside the chamber, because right now the gas flow rate is not so important. We already have so many precursors, right? We already have so many precursors, so we can stack wafer together, okay? So right now, we use the figure to show you what does that mean, stack wafer vertically. You see the picture from the page 29. So this is the tool for the LPCVD. You see the reactor just the same as the furnace, right? You see this is the same as the furnace. So right now you know for the furnace, FURNACE, for the furnace, it can do the oxidation. And for the furnace, it can be used for the LPCVD, okay? Only the LPCVD, okay? Furnace, this is the tool for the furnace. The furnace can use the oxidation, right? Furnace can also use for the LPCVD only, okay? Not another kind of CVD, only LP, low pressure CVD, okay? So you see, today we can stack, today we can stack silicon wafer very closely, horizontally or vertically, and it's closely because gas flow is not so important, right? Because we already have so many precursors, so the uniformity of the gas flow is not so important. So I can put each silicon wafer so closely because we already have the sufficient precursor, okay? 因为在 LPCVD 的机制里面，我们已经有很多的 precursor， 对不对？因为它中间，它这边是有抽真空，所以里面没有空气，所以它的 precursor 已经可以到达这个 wafer 的每个角落。所以今天我有没有必要把这个 wafer 平坦的放？没有嘛，我可以尽可能的把 wafer 都放得很近，因为 precursor 它的 reactant 这些反应物已经在这个 silicon wafer 表面已经有足够多了。所以今天我不用把 wafer 把它平着放，我把它全部立起来，水平立起来，垂直立起来，放得很近都没有问题因为它表面的 precursor 够多了对于 LPCVD 而言，决定它的 growth rate 是谁？是温度是温度，是 reaction rate， OK？ So today we can put the silicon wafer vertically, horizontally, and the most important is the closely, because right now we already have sufficient precursor, right? We have a lot of precursor, so the gas flow rate and the flow rate uniformity is not important for the LPCVD, okay? And you see how this tool is furnace. Furnace can be used for the oxidation and also for the LPCVD, okay? So just like the furnace, this is the silicon wafer, this is the silicon wafer, right? And we use the coil, to heat. We use the coil to heat the vacuum, to heat the quartz tube, So the whole chamber, the whole quartz tube has the uniform temperature, right? So we mentioned for the furnace, it's the hot water system. We say it's the hot water system, and the temperature uniformity is good, right? Because the whole chamber, the whole vacuum, the whole quartz tube has the same temperature. So the temperature uniformity is also good, right? Because we use the coil. This coil is surrounding this quartz tube, 石英管. The coil is surrounding the quartz tube, and the whole quartz tube has the uniform temperature. So that's a reason we say the furnace is the hot water system, okay? Because the whole chamber, the whole quartz tube has the uniform temperature, okay? And also, one time, we can deposit so many silicon wafers. So of course, it's the batch system. It's a batch system. BATCH. It's a batch system. It means one time, we can deposit so many silicon wafers. So it's the batch system. Okay. So it's just like the furnace. It's just like the furnace. Okay. So right now, this reactor operates in the reaction rate control because we have a lot of precursors, but we don't have the sufficient energy. So today, the uniform temperature is important. So that's the reason we use the tool of the furnace. Okay. So the uniform temperature is important, and also high temperature is also important. Okay. So uniform temperature and high temperature, it can have the higher growth rate and uniform growth rate. Okay. But you need to know for the furnace, one drawback for the furnace, is the particle. The particle will deposit on the chamber, and then when you heat the chamber again, this particle will fall down on the silicon wafer. So it's required this chamber, the chamber is a quartz tube. This quartz tube must require frequently cleaning, okay? Because the particle will deposit here. Usually the particle will deposit on the chamber wall, the particle will remain on the chamber wall. And then when we cool down and then when we heat again, this particle will fall down, the particle will fall down on the silicon wafer, okay? So that's the reason we need to do the cleaning. The quartz tube must undergo the cleaning frequently. This is the drawback for the hot water system. Usually hot water system, they will deposit some remaining on the chamber wall. And next time when you do the next round, this remaining will fall down on the silicon wafer. Okay, so this is the main drawback for the hot water system. Okay. 这个情况只有在 hot water system 才会有。通常我们在沉积的时候，一定是所有的 chamber 都会整个会沉积。所以不是你的 chamber 的这个墙壁或是的 wafer 上面都会沉积。那你的沉积物会同时也会沉积在这个 chamber 上面。但是我们的这个炉管通常是比较高温的一个制成。所以它升降温的过程当中，因为它是整个腔体都同时会升降温，所以当你的升降温过程当中升温降温后，你的 particle 就很容易脱落。那很容易脱落，当然就是掉到你的 silicon wafer 上面来。那如果一般是用 cold wall system， 像我们之前说的 RTA 的系统，它是不是只有部分的区域加热？它不是整个 chamber 的墙壁都加热，所以附着在墙壁上面的沉积物就比较不容易掉下来。那你如果是 hot water system， 你这个腔体可能都历经500、600甚至到800度的高温，上面的 particle 就很容易因为升降温，它就很容易就会掉下来，污染到你的 wafer。OK，let's take 10 minutes for break.